here we talk about complex roots and a very fancy name, the fundamental theorem of algebra. Well, it's the fundamental theorem of algebra says that if you have a polynomial, it has at least one complex root, some number c such that p of c equals 0. So you can always solve an algebraic equation, basically, which is good because you invented negative numbers and fractions and irrationals and imaginaries in order to solve equations you couldn't solve before. Now you can, so there you are. All right, now, since c is 0, p of c is 0, then by the work of section 3.4, where you factor out an x minus c factor from the polynomial, p of x is x minus c times q of x for q, some polynomial. This is called extracting a root because this too will have at least one root, so you get x minus d times another polynomial. And that'll be x minus c and e times another polynomial until you run out of roots. And so you get polynomial p of x written as a product of x minus root. And that's called complete factorization. So any polynomial of degree n is of the form a times x minus c1 times x minus c2 all the way up to x minus cn, where a and all the c's are complex numbers. And c1 through cn are the solutions, the roots of the polynomial. Now that means that any polynomial has of degree n will have n roots, but you have to count complex roots and you have to have multiple roots more than once. So if you have an x minus c squared, that's multiplicity 2 and you count it twice. If all the p's coefficients are real, so all the an's are equal to their own conjugates, then it follows fairly simply that p of a conjugate is a conjugate of p. So therefore, if p of c is 0, then p of c bar, its conjugate, is also 0. So if all the coefficients of the polynomial are real, then the complex roots come in conjugate pairs. For example, x squared, x to the fourth plus 5x squared plus 4. You can factor that to x squared plus 1 times x squared plus 4. This is the sum of squares, which will equal x minus I times x plus I. This is x squared plus 2 squared, which factors to x minus 2i times x plus 2i. So the roots of this polynomial, x to the fourth plus 5x squared plus 4 equals 0, will be plus I or minus I or plus 2i or minus 2i. Pairs of conjugate solutions. So, for example, find all the roots and of x squared, fourth plus 4x squared, and factor it. So x to the fourth plus 4x squared, you can factor out an x squared, that's easy. X to the fourth x squared plus 4, that's x squared plus 2i, which is the same as x minus 2i times x plus 2i. So the roots are 0 twice, x minus 0 times x minus 0. X minus 2i gives you a root of 2i, x plus 2i gives you a root of minus 2i. So these are the roots, 0, 2i, and negative 2i. And 0 has multiplicity 2. Now here, let's factor x to the fourth plus 2x squared plus 1. Well, all right, that's the square of x squared plus 1. And x squared plus 1 is x minus I times x plus I. Also, you have, since it's squared, you also again get x minus I times x plus I. So here's the factorization. X minus I twice, x plus I twice. So the roots are x equal to I or x equal to negative I, and both of these are double roots. So counting 2 plus 2, that makes 4 roots, and that fits this fourth degree polynomial. Factor x, let's do the same for x cubed plus x squared plus 9x plus 9. Okay, this one factors by grouping. X cubed plus x squared factors into x squared times x plus 1. 9x plus 9 factors into 9 times x plus 1. X squared times x plus 1 plus 9 times x plus 1. Well, the x plus 1 is a common factor, out it comes, times x squared plus 9. Here it is. X squared plus 9 times x plus 1. Now this is x squared plus 3 squared. Sum of squares, therefore it's x minus 3i times x plus 3i. And x plus 1 is x minus negative 1. So you can read off the roots. 3i minus 3i and negative 1. Here are, now let's factor x to the fourth plus 3x squared plus 4, minus 4. Okay, this first factor is x squared plus 4 times x squared minus 1. Okay, x squared plus 2 squared factors into x plus 2i times x minus 2i. X squared minus 1 squared factors into, x squared minus 1 squared is x minus 1 times x plus 1. So the roots are negative 2i for this, 2i for this, 1 for this, minus 1 for this. Now here's a reverse problem. Instead of given a polynomial, find its roots, here's given the roots, find the polynomial. And let's make it of degree 2, because there's only 2 roots required. The roots are x plus I times x minus I. So multiply product, x minus 1 plus I times x minus 1 minus I. This factor will be 0 at 1 plus I. This factor will be 0 at 1 minus I. So this polynomial should do the job. Okay, let's expand it. First, x times x is x squared. Outer, minus x times 1 minus I. Inner, minus 1 plus I times x. And last, 1 plus I minus I times 1 plus I. Okay, expand this, bit of arithmetic. Here we go, x squared minus 2x plus 2. And that's the polynomial. Now here, we want to find all the roots of x cubed minus 3x squared plus 3x minus 2. All right, it's not immediately obvious how to factor it, so what we'll do is use the tricks of the section 3, I believe it was, no, 3-4, where we find rational roots and bounds on roots and use synthetic division. Any rational root has to be the form of a divisor of this number, -2, over a divisor of this coefficient 1. And the only such numbers are plus or minus 1 and plus or minus 2. So there's 4 numbers to check. Let's start with 2. If you evaluate 2 at 1x cubed minus 3x squared plus 3x minus 2, we use synthetic division. Every time we go down, we add. Every time we go up and the right, we multiply by 2. Bring down the 1, there's a 1, times the 2 is a 2, plus a -3 is a -1, times the 2 is a -2, plus the 3 is a 1, times the 2 is a 2, plus a -2 is a 0. Good. So it's a root. P of 2 is 0. And we pull out a factor of x minus 2 times, read off the quotient from here, 1x squared minus x plus 1. So P of x is x minus 2 times x squared minus x plus 1. All right, so 2 is a root, and any other root has to solve this. X squared minus x plus 1 equals 0. And for that, you use the quadratic equation. Minus a -1 plus or minus -1 squared minus 4 times 1 plus 1 times 1 times 1 over twice 1. After a bit of arithmetic, it's a half plus or minus I times √3 over 2. So those are the roots. 2, a half minus I √3 over 2, and a half plus I √3 over 2. Now here's a monster. X to the 5th minus x to the 4th plus 7x cubed minus 7x squared plus 12x minus 12, find its roots. Well, okay, it's fairly obvious to see that these and these 2 and these 2 factor out in x minus 1. So you get x to the 4th times x minus 1 for these 2 terms, 7x squared times x minus 1 for these 2 terms, and 12 times x minus 1 for these 2 terms. Factor out an x minus 1 times x to the 4th plus 7x squared plus 12, like these. Now this, okay, this is a quadratic in x squared, and we need 2 numbers here and here, whose sum is 7 and whose product is 12. 3 and 4 work. So this, x to the 4th plus 7x squared plus 12 factors into x squared plus 3 times x squared plus 4. And all that, remember, is still times x minus 1. Now, all right, x squared plus 4 is x squared plus 2 squared. That factors into x minus I2 times x plus I2. X squared plus 3 is x squared plus √3 squared. And that factors x minus I √3 times x plus I √3. And great. We've factored it fully. And therefore P is 0. whenever each one of these factors is 0. X equals 1, which zeroes this out. X equals I root 3, which zeroes this. X equals minus I root 3, which zeroes out this. X equals I2, which zeroes out this. And X equals minus I2, which zeroes out that. So those are the 5 roots of this 5th degree equation. Now here we have a polynomial with a complex coefficient, but that doesn't really do much damage. Find its roots. Well, okay, in this case, there's a common factor of x times x minus I. And so this is 0 only with x is 0 or when x minus I is 0. That's the root. So the roots are 0 and I, and we're done.